don't have time for questions, and we proceed now to the last lecture today. It will be given by Professor Yuri Petrov, and the title of the lecture is Structure of Time, Nature of Dynamic Instability of Fracture Process. I think after this session, after this lecture, we have enough time for discussions.
Yeah, that is one I copied just a little while ago. Is that the one?
Yeah, the lowest one. Yeah.
Oh, okay, so I'll just back here.
Thank you, colleagues. Thank you, Chairman. I'm going to talk about dynamic fracture mechanics with respect to its relation to crack propagation problem. This is just a couple of well-known pictures which definitely demonstrate crucial importance of crack propagation modeling, if not to spend much time on motivation talk here. And this is an outline of my talk. I will. The main purpose of my talk is to discuss the crack propagation and the KV relation observations. Then I introduce the newly developed incubation time approach and corresponding simulation technique that would allow us to resolve some of the problems of dynamic crack propagations and to resolve some of the contradictions related to this phenomenon. The state of the problem arising from classic fracture mechanics associated with strength and fracture toughness. Strength and fracture toughness. It corresponds to the basic idea of the energy balance, so that we must have required energy released per unit of new surface to produce a fracture at the crack tip, and this is a specific energy ought to be material function. And the main result of elastodynamic analysis of the problem is that the stress field at the vicinity of the crack can be described by the square root singular asymptotical expansion, similar to quasi-static problem, and the singular part of near tip stress can be written in this case in this form, and the amplitude of the singularity is then characterized by the single parameter Kd, called dynamic stress intensity factor for the mode 1, and I will only talk about this case. And it is a function of time and the crack speed v. Applying Griffith's energy balance to elastodynamic solution, we complete the dynamic fracture problem state and provide the crack tip equation of motion, like this one. And here gamma is the fracture surface energy, and it is a material property to be determined experimentally, and just we must note that it may also depend on the crack position and the speed, and so it is very complicated functional that is proclaimed to be material function. And in terms of stress intensity factor notion, we can formulate the same in forms of the following equations, like this one. and where the right parts ought to be considered also as material properties. And there are two basic concepts. The first one is just for the crack start, can be used, and the second one is applied to the moving cracks. And there are two basic consequences from this analysis. First, it predicts that maximum speed which is possible for a crack is a relative surface wave speed. And second, it indicates that there is a unique relation between crack driving force characterized by the stress intensity factor Kd and the crack speed. So there should be a unique Kv relation, which is, as normally considered, ought to be taken from experiments and then incorporated in the theoretical modeling. Should be, but it's not the case. Why it's a problem? What we have in reality with the maximum speed, and does this unique relation actually exists? It turned out that many experimental observations of brittle fracture contradict both of these predictions. So nowadays there exists a big deal of confusion in interpretation of experiments on propagating cracks, and here I conditionally specified just 3 main points of view related to 3 types of classical tests. First, on the left side, is it seen? I'm not sure. Some of the scientists, like our classics, Irwin and Professor Daly, definitely support the existence of the unique Kv relation. Using dynamic photoelasticity and high-speed filming, propagating cracks in some materials like homolyte 100, like here, they have provided data in the support of that relation. But the second case, in the second case, we have a little bit different version provided by Professor Kalthoff, which these observations definitely question a little bit the previous conclusion. Here we have similar Kv curves, but we have not to note that it is not a unique Kv relation. Kalthoff's results show its dependence on specimen type or specimen shape or geometry. So it seems that it is not a material relation. So important, all these cases, first and the second one, are specified for slow static loads applied to the sample prior to the initiation and further acceleration of the crack. And the third case is on the left here. Ravich and Darn-Knaus employed the method of caustics with the same material, homolyte 100, like this one. And the loading of crack was extremely dynamic and produced by electromagnetic impact. And produced by electromagnetic impact with a duration with about 150 microseconds. And they utilized large plates to imitate the unbounded medium, and what they just got straight lines. So the result indicates the lack of one-to-one relationship between K1 and V. So according to them, they concluded that there is no such relation at all. It doesn't exist. And there are many heated debates among all these people up to nowadays, and all arguments concern the correctness of experimental methods and used for registration of, which were used for registration of fast fracture and interpretation of the data of experiment. But now I'm going to show how this instability can be interpreted in frameworks of the spatial approach based on the spatio-temporal discreteness of the process. My explanation is referred to the incubation time approach in mechanics of continuum. In the case of brittle fracture, it results in the following fracture criteria, like this one. And it utilizes two material parameters, d and tau, just two material parameters. Parameter d is size, is a linear size. It's just the size of a representative volume for given scale level. So just to specify the fracture event on the given scale level, we have to get this representative volume of the size d. And material characteristic time, we call this time period incubation time. And in many cases, it represents characteristic time of relaxation that accompanies the process of microcracking, that includes microcrack nucleation, growth, coalescence, and so on. All that preparatory processes that precede the macro fracture event. In many cases, it's just equal to characteristic time of relaxation. So eventually, it looks like quantizing the process in space and time, so that naturally leads to the critical structural momentum like this one. And now how it works. And here, there is an example of instability related to well-known unstable behavior of dynamic fracture toughness. So here, we have a special case of the previous criterion in this form. And let's now consider a mode 1 semi-infinite crack, like in the scheme of Norwegian laws, which is loaded by the pressure on its faces. And if I solve a dynamic boundary problem and utilize incubation time criterion, we can get effect of unstable behavior of K1D at the start of crack growth. The principal nature of such instability is related to the difference between high rate and short pulse loading. Why? So suppose that the load on the crack faces is acting up to the moment of fracture. So at this moment we have a value of fracture toughness, this K1 star, K1T. And it definitely happens usually on the increasing stage. And now I want to fix this T star. And now I want to consider the short pulse loading with the duration T, which is equal to T star. And so I want to write the equation. Can the amplitude be decreased while fracture events still remain? So can I decrease the amplitude with the retention of the fracture event? The answer is yes. And by this way, we can come to the threshold loading, like this one. So that any pulses of the amplitude less than this one will not produce fracture. But in this case, we will have a fracture on the decreasing stage of stress intensity factor. And the value of this K1D definitely will be different compared to the previous one in this case, so that we will have the scatter of K1D, and this is a yellow region shows you the possible the region of possible values of K1D corresponding to different ways of loading. This is a high rate loading and short pulse loading, which corroborates well with experimental observations by different authors. And so this is the first example of the instability. So this theory generally can be considered as some generalization of linear fracture mechanics. And let's now turn to dynamic crack propagation problem. This is the state of the problem, the mathematical state of the problem, with the scheme, numerical scheme, with the node release technique, which can be incorporated by the critical conditions like that. And we validated this technique on these two experimental schemes related to experiments by Feinberg and by Ravi-Chandar. And we got, after the validation, good preparation of the correct trajectory in time scale, like this one and this one. And now the question is, can we get something like it was received by Karpov in his experiments when he got these KV relations, which you consider is not unique. We just used simplified geometry in our calculations, like this one. And also we simulated the experiments of impact loading by Ravi-Chandar in this kind of geometry and this impact loading. And so, in the second case, we just got this straight lines.
We count maybe 2 minutes.
Okay, in this case, we just got these straight lines, which are very similar to what was observed in experiments. So in the second case, we got these two curves, but it's important that fitting was applied to get these continuous curves. What is fitting? This is a hypothetical material which demonstrates what is happening actually. So when we dealing with the slow loading rate, we also have a scattering, the K1D, and we also have a discrete values of the velocity. But we can fit just to get a dependence similar to classical. But in this case of impact loading, there is no sense in fitting, and we should consider it as a principal feature of the fracture process related to its discrete nature and its spatial temporal discreteness. And my conclusions is that theoretically often pre-extensions history are closely following those observed experimentally. All variants of K1V dependence behavior will be obtained using unified approach. And scattering of this stress intensity effector values is considered as a feature related to discrete or quantized character of the crack propagation process. And the size of the scatter determines if it is possible to construct classic KV curves. Sometimes it's impossible. And so incubation time approach is shown to be applicable to model effectively crack propagation for a wide class of problems and to resolve some of the contradictions I talked about. Thank you.
Thank you very much. Thank you very much, Professor Pedro. Thank you all for your contribution. We managed just to complete our session in time. So we have now plenty of time for questions, at first for this lecture, and then for previous lecture, if you wish. And what we also can do, we can continue, you can always continue discussion over coffee break, but there is no coffee break anymore, so, so it's, if you like, you can discuss after the session. So, do we have any question for this lecture now? If not, then I would ask one question. I always wonder, ask myself, and I never tried, how much do K depend on knee? For example, if I change knee from 0.3 to 0.33, will it affect K values or not?
Depend on, depend on, you mean,
yeah.
Which parameter do you mean?
This one which you mentioned here. Also, yeah.
K depend on,
yes.
no, but it's V.
V, okay.
V. So
that's
it's K V depends.
Okay. So, do we have any questions for other previous lectures? If not, so please don't hesitate, contact, but I will not leave you go from here before I give you another information. We are organizing one conference in Dubrovnik in October, and same conference will be organized next year in June. So I will just use this opportunity, particularly from colleagues from very far away from Japan, to join us next conference. If you might be interested, you have already. Please do not hesitate to distribute this among your colleagues. It's for you.